Yeah, thanks for the intro. Hey everyone, I'm Nick. I'll be talking to you about neural networks in TensorFlow 2.0. So this will be a pretty chill interactive session. I'll mostly be live coding on this document here. So please feel free to interrupt, ask questions. We can take as long as you guys like on any topic. I don't expect to get through all of it. But if you guys are interested, the notebook is available at this link here. And so you can see the completed code with explanations there. So don't worry about writing anything down now. And yeah, so just a quick overview. We'll be talking about what TensorFlow is. Then we'll move on to linear and logistic regression, which are basic techniques. We'll talk about an algorithm called gradient descent. And then we'll finally get into talking about neural networks and what the TensorFlow library can do for you. Cool. So to start, what is TensorFlow? So TensorFlow is an open source numerical computation platform, which is mainly designed for machine learning. And so compared to things like NumPy or SciPy, which are other Python libraries, TensorFlow offers some hardware acceleration, so you can run things on the GPU or other kinds of devices, and also automatic differentiation, which we'll see what that is a little bit later and why that's important. This recent update for TensorFlow 2 has changed the API a lot, and it's actually a lot more usable, which is why I chose it to present today. And also talk briefly about what I'm using. I'm using something called Google Collab. So this is literally like a Jupyter notebook in your lab, in your browser, if anyone's worked with this before. So essentially you have cells, it's interactive. You'll see why it's pretty useful. And the nice thing is you can use this yourself. And if I can find it, runtime. So you have access to hardware acceleration. So you can use either a CPU, a GPU, or a TPU, which is great because you normally wouldn't have access to a GPU, but here you have free access. Cool. So we can just get started. First thing is importing TensorFlow. So in Collab, you want to do this to import the newest version of TensorFlow. And you have the library. And so the key unit of computation in this library is called a tensor. And you can think of a tensor as basically an array, but a multi-dimensional array. So a quick example is here you can convert a list to a tensor. It connects, boom. And so here you have a tensor. You'll notice a couple things. Tensor has an ID, and so every new tensor that's created will get an ID. That's not too important. It has a shape, a data type, and so whether that's integer, floats, etc., and you have the actual values. And so if you want to extract the value out of this tensor, you can just do .numpy, which will give you a numpy array to work with. So these are a lot faster than Python lists or arrays for many reasons. Firstly, it's implemented in C in the backend, and so any operations you want to do are very quick. But another thing is it supports vectorized operations. And so what that means is, for example, in Python, if you wanted to multiply each element of a list by 2, you'd do a loop and do each element. But in something like TensorFlow, you can just do something like that, and that'll multiply every element of the list by 2 for you. And you can also, multiply by 2, add 1, and that works great. The last thing that's really nice about TensorFlow is a property called broadcasting. And so this is pretty common across a lot of numerical computation libraries. Essentially, it's very similar to vectorization. It allows you to do stuff like this. So if you have a vector here, 1, 2, 3, and you have a matrix, so 3, let's say 4, 5, 6. Broadcasting will basically allow you to add the vector to the matrix, and what will happen is this. It'll check which dimensions match, and whichever dimensions don't match, it'll actually duplicate the vector. Don't worry if you didn't catch that, or if you don't quite understand what's going on. I did post a link in the completed document to read about this in more detail, but we will use this property for the rest of the workshop. I guess some final things. A tensor is something that's immutable. You can't change it in Python. So if you want to work with some kind of array that you can change, you have to use something called a variable. And so v equals tf.variable. This can be an array, or it can also just be a single value here, if this will work. And so, yeah, the shape is none because it's just a scalar value. It's not an array. It has a numpy value. You can assign it to a new value, assign a new value to it, and that changes as you see. So that's just a basic introduction to TensorFlow. Any questions about stuff that I did? Great, cool. So one thing I mentioned was TensorFlow is an open source platform for machine learning. So I guess the first question is, what is machine learning? And so I'm going to talk about a specific kind of machine learning today, and it's called supervised learning. And essentially, you have some input x, and you're trying to predict some target variable y. And that's like basically in the most basic form. And a simple example would be a line. So you have some data, like your x variable, and you want to predict the y. You can just simply fit a line, y equals mx plus b. But of course, this is a very simple version. You can do much more advanced things, anywhere from recognizing animals and images, or understanding if a sequence of text is like positive sentiment or negative sentiment. So really, these techniques scale up to very complex tasks that are useful to many people. So the first thing we're going to do is talk about linear regression. So the structure of this workshop is basically we're going to build on some very fundamental basic building blocks, and eventually build these up into complex systems and eventually neural networks. And so I just want to make sure that every step of the way everyone understands what's going on, because we're always going to be building on things that we've done. Cool. So let's just generate some x data here. So we can do tf range will generate values between these two numbers, and 0.1 is the step. Oh, that's text. That's not code. So here we have a sequence of values here. And then now let's just generate some random data and let's simulate a line. And so how can we do that? Let's simulate the line y. We want y equals 2.5 times x minus 1, for example, a simple line. And so we can do that. Y equals 2.5 times x minus 1. And I mentioned vectorized operations before. This will do it on all the elements of x. Let's also generate some random noise. And so we can do tf.random. And we know there's 40 elements in the other one, so we'll do shape equals 40. Min val. So basically wanted to generate values from -1 to +1. Cool, and we can actually take a look at how these two values compare. So there's a library called Matplotlib. It's a very useful plotting library. I won't go into too much detail here. We're just going to use it to see some points. Line. Oh, that's not what I wanted. Cool. So exactly what we generated, we just generated some points. Now our goal is we're going to fit a line y equals mx plus b to this data. And so let's create some variables. So m equals tf.variable. Let's say 1. So here's our goal. We're trying to fit a line y equals mx plus b. And the way we're going to do this is we're going to assume that y and x are fixed, of course. That's our data. And our variables are m and b. We're trying to find the best values of m and b. In machine learning, m and b are called parameters. And these parameters are what we're going to fit to our data. And so let's take a look at how this looks before we fit the values. And so that looks like that. And then we can actually see how the line looks. Oh, that's not what I wanted. M times x plus. So yeah, obviously this line is not doing a great job. So the first thing we need to do before we can fit this line to the data is understand how wrong our line actually is. And we need some kind of numeric measure to do that. And typically for regression, we use a metric called the mean squared error. And I'm going to cheat and copy and paste some text because I'm not typing all of that out. Cool. So mean squared error looks something like that. Essentially, you're taking the squared distance between the true value, so our data, and our predicted value, which is a line here, and squaring it and taking the average over the entire data set. And so in order to fit our line to this data, we want to minimize this value. So let's actually create a function, define MSE, where we can compute this for our data. So if you want to take a sum or a mean of a vector in TensorFlow, usually it's reduce something. So you can see here, like there's a bunch of different operations. The one we're going to use is reduce mean. And because we have vectorized operations, we can just subtract the true value from the prediction and just square that. Cool. I'm also going to call our predictions ypred, and that's just equal to m times x plus b. So let's check this out. MSE of our predictions and our true values. Oh, it's probably the right order. Cool, and so it's 14 right now, and basically we want to minimize this value. So if you guys are familiar with linear regression, you guys know there's a closed form solution for this. And so I'm just going to type this out. Actually, I will not type it out for the sake of time. Hold on. Cool. Just for the sake of time, I won't type this out. But essentially, we are computing some values, and we're assigning these variables a new value. And now we can see that the loss is much smaller, and then we can also visualize how this looks as well. So if we plot the original data and also plot our line, x times m plus b, we can see that our line fits our data really well. And we did this by minimizing our mean squared error, which is our measure of how poor our line is doing. And we can also check out what these actual values are. 2.44 and negative 0.89, pretty close to what our original values were. So that's like a basic primer on linear regression and what kind of an introduction to machine learning looks like. Any questions about this stuff? No? Yep.
Can you go over the code and copy paste it?
Yes, sure. So yeah, this is not too, the actual formula for the closed form for linear regression is not too important for this workshop, but essentially I can explain exactly what's going on here. Yeah, exactly. And so essentially this is the average of the data, and we're taking the sum of the squared errors here. Yeah, I won't go into too much detail, but yep. Oh yeah, so you can actually check it out now and follow along if you'd like. It's just this link right here. That'll take you to a GitHub page. You can open this in Collab. Sorry? Yep. And then so at the top of the page, there's like an open in Collab button. Actually, let me just show you. So, yeah, so you can, it'll lead to a GitHub page, and then you can just click open in Collab. You might have to like control click it. Sometimes it doesn't work too well. And it will hopefully, yeah, pop it up here. And so, sure. Yeah. Cool. So, great. So now we looked at just fitting a line to data. And so now there's a question. So I showed you there's this closed form solution to calculate the values of m and b for this line we want to calculate. But we're going to soon see that there's not always a closed form solution for what we're trying to calculate. And so we have to find a way to find the true values of these parameters, m and b, or whatever our parameters may be, when we don't have a closed form solution. And an algorithm to do so is called gradient descent. And so the idea is as follows. I think it's kind of summed up in this picture pretty well. So you have some parameters, let's say it's like theta 0 and theta 1. And so you have the lost value, which is like j as a function of theta 0 and theta 1. So in our case, that was mean squared error. And it's high for some values of the thetas and low for other values of the thetas. You want to find the values of theta for which the function is minimized. And so if you travel in the direction of the negative derivative, you're kind of decreasing your function. And over time, you're kind of following this path to reach a local minimum for your function. And so this is the strategy we're essentially going to use to fit our parameters to our model. So of course, there are some caveats to doing this technique, right? The first thing is it's not guaranteed to find a global minimum. Like even in this picture, you can see that the best solution is the one pointed by this red arrow, but the gradient descent algorithm only finds this one. And also, it's much slower. That closed form solution, it was just a couple lines and a very fast computation. But this is going to be an iterative process where we follow the direction of the gradient until we get to the bottom. Luckily, in the case of linear regression, the function is what we call convex. And so there's only one minima that it'll reach. So we'll always find the best solution. But we're going to see soon that this is not the case for most situations. Any questions about gradient descent? We're going to implement it right now. So we'll see how that goes. So here's the update rule. So basically, this is going to be like in a loop. We're going to do this in an iterative process. The new value of m is just basically going to be the old value subtracting the derivative. And we have this scaling factor here called the learning rate. And so basically, this is some small value to make sure we don't take huge steps. We want to take small steps towards the bottom of our loss surface. Because if you imagine if we take a huge step, we're totally going to miss the bottom. And overshoot. Cool. All right, so let's start implementing this. So again, once again, we'll make these variables m and b. For variables, you can also set the data type, and I'm going to set this to float 32. I would recommend when you're using TensorFlow to set the data type, even if you know it's like supposed to be an integer or something else. You'll notice that TensorFlow complains a lot about types. For example, if you have a 64-bit versus 32-bit integer, there are situations where it may complain. And so just setting the D type just avoids all that hassle for you. And so once again, we have our variables. And we're going to talk about one of the most important parts of TensorFlow, which is automatic differentiation. So essentially, TensorFlow can take derivatives for us. We don't have to compute that by hand, which is one of the main reason why it's used for machine learning. And so here's how we can take advantage of that. We open up something called a gradient tape. I will type in the code and then I will speak. And so we have a prediction here, which is exactly what we were talking about before, x times m plus b. And then so we talked about a loss function, which describes how poor our model is. And so that's exactly mean squared error, where we have our y true is equal to our y, and our prediction is equal to our prediction. Okay. And now we can take the gradient with respect to the loss. Oh, I should probably explain what a gradient is. Cool. So I will come back to that. But so I talked about partial derivatives, and so we have this loss function. We're taking the derivative with respect to the parameter. A gradient, which I'm going to denote by this nabla L, is basically a vector of partial derivatives. And so if you have your parameters like m and b, the gradient would be the derivative with respect to m and b. It's just simply just the derivatives of the ball. And so TensorFlow here was able to calculate the derivatives at these values. And in particular, for m, it was just minus 23, and for b, it was minus 6. And so our algorithm is basically going to follow this direction of this derivative until we minimize our loss function. Any questions about why I did this or how I did this? Cool. So let's actually write this. Oh, question? No? Good. Cool. So we're just going to write a for loop and make this happen. So I talked about a learning rate before. So typically, this is something you would have to tune later or find good values for. I'm going to just use 0.05 here because I know it works for this. We can talk a little bit more about how to choose that later. We're going to take, let's say, 100 steps. And once again, I'm just going to copy and paste this. So exactly what we had before. Oh, sorry. Where we're computing the gradient, and here we're going to store that. And now we're going to travel in the direction of the negative gradient, exactly what I said before. So we assign m minus learning rate times the derivative for m, and we're going to assign b minus learning rate times the derivative for b. And now we can also just print out, every 10 steps, we'll just print out what the loss is looking like. So cool. So a quick note, maybe you guys have not seen this before. This is a format string in Python. Super useful. Essentially, it allows you to just insert Python codes right into your string. Super easy. And yeah, so this is exactly what we wanted. We have this loss function here, and we want to minimize this loss. And by traveling in this direction, we have decreased our loss to about 0.27. And now our parameter values are pretty close to what we wanted. They're not perfect yet, but if you kept going, they would get really close. Cool. So any questions about what I did here? Great. Yep.
How do you pick the learning rate?
Yeah, good question. So it depends on the problem. I won't talk about it for linear regression, but later when we talk about neural networks, we'll talk about learning rate a little bit more. It's very problem dependent. There are some good ranges, like 0.01 to about 0.1 to the -4 are like good starting ranges. We'll see later that you may want to change your learning rate over the course of training. So what I'm doing here when I'm fitting this model, I'm going to call it training. We might want to decrease it over time because if you imagine as you get closer to the bottom, you want to take smaller and smaller steps. Something we'll definitely touch on a little bit later as well. Anything else? Cool. So I do want to talk about, oh, well, I guess before we move on, let's make this a little bit more nicely structured in terms of code. And so right now we have just created these variables and we created these tensors. It's kind of all over the place and it's not going to scale well when we talk about bigger models. And so I'm just going to encapsulate all this in a class. And so essentially how this is going to work is, does anyone here not know how Python classes work? Cool, great. Okay, so I'm just going to assume that you guys know what's going on. So we're literally going to do the exact same thing. Cool. And I'm going to create a property called trainable variables. And you'll see why this will be helpful to us a little bit later. Cool, so we have the variables that we want to use in our model. And I'm also going to define this dunder call method. And it's going to take as input some variable x. So dunder call essentially lets you use the object as a function. If you're not really familiar with how that works, we'll see how that works very soon. But essentially, we're going to return whatever the result of the slope multiplied by x plus b. And so this is going to make our training loop a little bit nicer. Oh, oops. Because we can do the following. Now we can define some linear model to be our linear function. Equals linear. So now this is super easy. All we have to do is call this linear model on our input. And instead of keeping track of m and b, we can just do linear model.trainable variables. And yeah, let's also take care of this. So we can also do the following. So yeah, sure. So basically, we're going to apply the gradient to each respective variable. And so we can just take the gradient and the variable. So we have the gradient here. Variables. And so we're going to do exactly what we did up here, where for the variable, we're just going to assign the, variable minus the learning rate times the gradient. So just to see how this goes, oh, nope. Great, so this is the exact same thing. Any questions about this part right here? Great, yeah, this will be a very useful tool for us going forward. We're also going to do one more thing before we move on. We're going to make something called an optimizer. And so I told you that gradient descent is the optimization algorithm we're using. When I refer to an optimizer, it's going to be an object in Python that does this for us. And so just to make things a little bit more clear, I'm going to create a class called gradient descent optimizer. It's going to look like following. So we're going to have some initializer, which just takes in the learning rate. We're going to give it a default of 0.05. And we're going to make a method called apply gradients. And this is essentially going to do exactly this. It's going to take in some gradients and variables. Then do this exact loop right here. And we need a self here. No. Cool, so that just makes our training loop a little bit more clean, where now we can just do the following. Instead, we can just apply the gradients to our linear model. And we're just going to have to create the optimizer here. Sorry. Oh no, self is not defined. Oh, okay. I shouldn't have done this. This is just already zipped. Cool. So this is what I want. So essentially, I just made this object here that does this computation for us. And the last step is, turns out TensorFlow already has this object, and we're just going to use that from now on. So from TensorFlow keras optimizers, we have something called SGD, and this stands for stochastic gradient descent. I'll explain where the stochastic comes from a little bit later in this talk, but literally we can just, it's a drop-in replacement, and it does the exact same thing that we want. Cool. So any questions about that stuff? Great. Okay. So now we're going to make this a little bit more general, right? What if we have multiple inputs and we want to fit a line to multiple inputs? So suppose you have some vector x of inputs, right? And so an easy example is, oh, suppose you want to predict the price of housing. You have multiple factors, right? The size of the house, the quality, how many bedrooms, etc. Multiple variables, one outcome. And so this is the basic formula for that. This is the same as a dot product. I'm assuming that you guys have taken some linear algebra, and so that just expands to this. So now the question is, okay, what if we also have multiple outputs? And so now your y is a vector and your x is a vector. And so now we have a weight matrix instead of just a vector. And so that, you don't have to worry about it too much, but it expands into this, where we are basically doing a linear combination of the x's to get each of the y's. So for this case, we're just going to update our linear model here so it supports multiple inputs and multiple outputs, because we're going to be using that very soon. So here, the key difference is we want to have an input length and an output length. And essentially so tf.1s, I'll show you what that does. Let's say like 3, 4. It basically creates a matrix of ones, and that's exactly what we want. Where one side length is the input length and output length. I'm not going to go through the exact math of why these dimensions, but when you do the matrix multiplication, this works out. And here we're going to do just zeros, and we want it to be the height of the y vector. And so that's just going to be output length. And so now we're going to talk, I'm also going to rename this W just to match the notation that we've already established. And so now we're going to talk about the matrix multiply operator in TensorFlow. And that's literally just the @ symbol. Cool. And so you may be wondering, okay, so why did I multiply on the left side versus the right side? We will see that, first of all, x transpose here, that's a row vector. And so for the dimensions to work out, you're multiplying a row vector by the weight matrix. Here, this input is also a row vector, which is why we're multiplying it in this order. Any questions about this modification here? Great. Cool. So now we're going to get into something a little bit more interesting. We're going to talk about a data set called MNIST. And so MNIST is a set of a bunch of handwritten digits. It was collected by these 3 researchers way back in the 90s, and this is a very common image classification benchmark. And so we're going to use this data to fit some models to identify if an image is one of 9 digits. And so let's just import this from TensorFlow. Oh, it's downloading. Cool. So here's an example of one of the images. So I'm using Matplotlib here just to show the image. Here's one example. So here, yeah, like this handwritten digit is a 3, and the Y label also claims it's a 3. So I was going to make you guys do some exercises, which involves like manipulating some of this data and looking into it. But I guess like most of you don't have laptops, so it's okay. We can just skip that. So one thing we're going to do now actually is, sorry. We are going to do some pre-processing. So we're just going to turn these into tensors. So right now they are NumPy arrays. We want to do the tf convert to tensor. To tensor y. Great. And so here's the exercises I was going to make you guys do. So essentially, what are the shape of the images? Once you run the cell here, you can see the exact shape. And so 60,000, it means that there are 60,000 different training examples, and each image is 28 by 28. Same here, there are 60,000 labels here as well. We can also count how many of each we have in this data set. I can write this again, so it makes more sense. So we know it goes from the numbers 1 to 10, and so essentially what I'm doing here is, first thing I want to do is check. So we want to check if which y variables are equal to I, and so we can actually look at how this looks as well. Y equal to 0, for example. This returns like a Boolean array, where it's true if it actually is equal to 0 and false otherwise. And so, for example, we know that the second example in this training set is actually a 0. And so what we're doing here is casting this Boolean array into integers. And then all we want to do for each one is take the sum of how many of those there are. And yeah, so you can see that there's pretty balanced. There's about 6,000 of each, which is good. So typically when you're doing machine learning and you have some task like this, it's very important to explore your data and understand exactly what's going on. That's not the focus of this workshop, but you should be looking into these things. And finally, we can just understand what data types there are. Cool. So any questions about this data? Great. So just to make it a little bit easier to work with, we're not going to do the whole 60,000, but instead we're just going to work with 500. So x is equal to x up to 500. Indexing in TensorFlow is almost exactly the same as it would be in Python. And one other thing, we noticed that the data type for x was integers. We're going to want these to be floats, and so let's make that happen. Casting, basically changing one type to another, and divide by 255. So why did I do that divide by 255? Image pixel intensities are values from 0 to 255. Typically in machine learning, especially what we're going to be doing now, it's nice if your features are kind of in a reasonable range. So like from 0 to 1 or -1 to 1. This makes a lot of things a lot easier to work with. For example, learning rate is a lot more predictable when you know the scale of your features. Things like, and it's just a little bit more manageable. So for those reasons, I guess I didn't elaborate too much. We are going to scale the inputs here. Now, we notice that y is values from 1 to 9. So when we were doing regression, when we just fit a line to the data, that made sense, right? Our y was some continuous value. So for example, if you're trying to predict a housing price, that's kind of a continuous value. But here, these are not continuous values. These are 9 different categories. And so it doesn't really make sense to fit a line through 9 different categories. Instead, we're going to do something called one-hot encoding. I'll show you what that is, and then I'll explain why we do it. So it's pretty easy. tf.onehot, y, depth equals 10 means that there's 10 different classes. Okay, yeah. It's cool. And so if you look at y0, for example, so now this has become a vector of length 10, and the only one is basically what the value was before. So this looks like it was, so this y was a 5 before, now it's a 1 here. So here's why we do this. Essentially, our model is going to predict what the probability is that a certain image is some number, right? So it's going to give us a probability that this number is a 0, this number is a 1, this number is a 2, etc. We are going to design a function that tells us how off our model is from the true examples here. And so here, this is like the ground truth. It's a 100% chance that this example is a 5. We know that for sure. That was in the data. Our model's not going to know that. Our model is going to predict various probabilities for the rest of the numbers. And our goal is going to be, let's bring these two distributions as close as we can. Our model should think that an image is the same thing that the true data actually says. That was maybe not the best explanation, but I do have a link in the Collab. So if you have more questions about why we do this, you can definitely check that out. But does anyone understand what the one-hot function does? Awesome. Last thing, we know that x here is a 28 by 28 image. In all of our examples before, we were working with vectors. And so what we're going to do is we're just going to flatten x into a long vector. And we do that using a reshape function. So we're reshaping x to the following dimensions. So essentially what the -1 does, okay, so we want to create vectors of length 28, 28 times 28, which is 784. So essentially we want to create vectors of length 784. This -1 indicates, okay, I don't really care what this number is, just whatever the rest of the data fits into, that's how many we need. And so we know there are 500 examples, and so that dimension ends up being 500. So now each of these vectors of length 784 represents one image that we had before. Any questions about that? Okay. I'm just going to copy and paste a quick function here, which is the preprocess function. We're going to keep this in our notebook because we are going to use it later. But essentially, this does everything I just did. Okay, cool. Now let's just make a linear model, exactly what we've been doing. So I'm just going to call it linear. And this is going to be a linear model where the input length is 784. And the output length is 10. So this is the class that we made before. And we can do linear on, oh no. Unexpected keyword input length. Sorry about that. Let me just fix this. Oh, we didn't run this. That's why. Okay. Cool. And so we can just, we have some random linear model and it gives us some output. I was telling, so the length of this output, if you look at just the first example, this is a vector of size 10. And I was telling you before that we want these to represent probabilities. And so we want to know what's the probability of it being the 0th digit, 1, 2, etc. And these are clearly not probabilities because they are numbers that are greater than 1. And so we are going to fix that. We're going to normalize these, but we're going to normalize in a special way, which involves some more copy and paste. Here. So we're going to use something called a softmax function. And so this is the softmax function here. Basically, it takes everything to the exponent and then just normalizes that. You don't have to worry about this exact form, but you just know that it normalizes these things. And so you might be curious about why we're using this function instead of straight normalizing. And so by normalizing, I mean taking the sum of all the values in the vector and dividing by each one by that sum. And the reason is as follows. The exponential function, it makes large values larger and it makes small values like a bit larger. And so it exaggerates the effect. And so if our model is making some predictions about, oh, it should be a 2 or a 3, and there's slight differences, this function will make sure that any slight difference is exaggerated. And so if it's slightly more sure about it being a 5, the 5 will be pushed a lot closer to 1, and the rest of the values closer to 0. And this will essentially help our model match the actual data that we have. And so let me just write that in Python and show you how that looks. So we have an exponent function in TensorFlow, and then we're just going to take the sum of all the elements. So we're doing axis equals 1. If you just do a reduced sum and we have some matrix, it's going to take the sum of everything in the matrix. When we say axis equals 1, we're just taking the sum of each of the rows, which is what we want here because we're only worried about each example. And so if we do a softmax on our linear model, Okay, I'm not 100% sure what's wrong with my softmax function. It worked on my other one, but we can just use TensorFlow softmax function. Something's wrong with my dimensions. That's okay. So now we can see that this vector represents some probability distribution. And so we can confirm that by just doing a tf.reduce sum on the first axis. And boom. So we can see that all the example vectors added up to 1, which means it's a probability. Great. So any questions about what we just did? We'll see this model in action very soon. But any questions about the softmax or why we used it? Awesome. We're going to define a couple more things. So before we were doing regression, we just measured how close our line was. Now we're doing classification. We have to choose one of several categories. And so for this, we can define accuracy. So exactly how many we get right. And so we're just going to define that in the way that you'd expect. We have our true and we have our predictions. And basically, we were trying to see which predictions are equal to. So argmax basically finds the position where the probability is the most. And so as we talked about before, whichever probability is the highest, that's our model's prediction. This function will return which index is the highest. And we're basically checking if that's the same as for y true. And in order to calculate the accuracy, we're just going to take the average of how many are right. Actually, this might be a little bit more clear if I type this out outside of this function. Let me actually do that. So I'm going to make y preds equal to this. And I'm going to make y true is equal to our y. And so here, so first I'll do this block of code. So for all of these, so you saw before that it was just all the numbers are equal, and so the argmax is just 0 for all of them. If you look at y true, these are like the correct indices of which index is the correct one. And so basically we're checking which ones are the same. Again, this is a Boolean array of true and false. And so we want to cast this to an integer, or I mean a float, because we're taking an average later. Cool, and I won't type out the rest, but essentially we're taking an average here. And so we can check the accuracy of our current model, which hasn't been trained. And so we can see it's 10%. So it's always predicting 0. It's the same accuracy as like some naive model just randomly guessing between 1 and 10, right? We haven't fit this to any data yet. Any questions about how I did accuracy? Cool. Yeah. The last thing we're going to have to set up before we can actually fix this, before we can actually fit this model is our loss function. So before, when we were doing regression, when we were fitting a line to our data, we used mean squared error, which made sense. Like, how far is this line from the actual value it should be? Here, that doesn't make so much sense. What we have here is we're comparing two like probability vectors, right? Where our model's guessing what the probability of each number is. Our true label is also a probability. Mean squared error doesn't make too much sense in this situation. We use a different function. And this is going to be a little bit more copy and paste because cool. I'm just going to copy and paste this stuff. Great. So this is the function we're going to use. This is the loss function. This is called categorical cross entropy. And it's as follows. And so if this is like the cross entropy for one example, so we know that we have a vector of like y1 to yk. For mness, that's like y1 to y10 because we have 10 different classes. And we are computing this function. This workshop is more practical. We're not going to go into the math of exactly why we use this function, but you can think of this as measuring the distance between the two distributions. And so in particular, we know that this y true is going to be 0 for most values and 1 only for the correct class. And we know this value here, the log of this y, it'll be 0 when we get when the value is 1. And if it's not 1, if it's less than 1, it'll be some negative value. And so essentially what this says is that, oh, this loss will be 0 when our model's predictions are the same as what the data is saying, which is exactly what we want. So yeah, this workshop is not about the math too much, but any questions about this math? All right, cool. So let's just define this as a function as well so we can use it. It's called categorical cross entropy, y true, y predictions. And this is basically exactly what you'd expect. tf.reduce sum times exactly the formula I typed out. Again, axis equals 1. Because we don't want this sum to happen over the entire matrix, we want it to happen over each example. So we created this function, but of course TensorFlow gives this to us too. It's called tf.keras.losses. It's a long name, but this is exactly defined as that. We are not going to use the function that we defined. Instead, we're going to use this function. Because it's a little bit more numerically stable, we will get better results. If you want to hear the details about those, we can definitely chat later. But yeah, let's just jump right into fitting this model. It's going to be the same as what we did before. We're going to create this optimizer, SGD, with our learning rate equal to 0.05. We're going to create a linear model, which is 28 by 28 input size, and then our output is 10. We're going to do 100 steps. We're going to open up this gradient tape so we can track our derivatives. So we are applying the linear model to our data, and then we're applying the softmax function that we talked about before. Then we're going to compute the loss per each example. So before mean squared error, it just did it over the entire data set. This loss is computed per example, and so we have a loss per example, which is, so we're just going to use, Now we're going to do categorical cross entropy with y true is equal to y true, and the predictions equal to the predictions. And now we're going to get the overall loss, which is just going to be the mean of the loss for everything else. And yeah. So once again, we're going to calculate the gradient with respect to the loss, and we want the linear model's trainable variables, which is, if you remember, just a weight matrix W and our bias B. And we're just going to apply the gradient like we did before, which is just a zip of the gradients and the actual variables. I'll just type this out too. And again, once again, we're going to print this loss every 100 steps. Next time I won't type this out again, I will just copy and paste it, but I hope that some typing out to help you follow. So once again, we have the loss, which is just a NumPy value, and we're actually also going to print the accuracy of our model, which is just the accuracy that we computed. Y true equals Y. Cool. No, there we go. Oh, I probably won't by 10. Oh, let's do it. So we're going to do 1,000 steps. This will take a little bit longer to fit. But as you can see, our accuracy shot up pretty quickly. Oh. And so this is doing great. Right? We just fit our model using gradient descent, and our data is telling us that, oh, this simple model has a 98% accuracy of recognizing digits. And so let's actually check this out. So let's actually just check out an example to make sure that's right. 0.numpy ypred. So yeah, here the largest value is 75%, which is the 1, 2, 3, 4, 5. Yeah, and it seems to be in the same position, and it seems like it's doing well. So what's going on here? It's kind of sus that halfway through the workshop we already get such good results. And so really the problem is this. We're evaluating our model on the same data that we trained it with. So this is the equivalent of if you have a student and you're teaching them a subject and you want them to write a test to see how well they're doing, imagine giving them the test as the preparation materials. Yeah, of course they're going to ace it. They're just going to memorize what's going on. And so it's essentially what's happening here. Our model is just memorizing the data I gave it. And so of course it's going to do really well. So how do we tell how well it's going to do in general, like on data that it hasn't seen before? And so we use something called a test set. So we have a training set, which we fit our model to, which we're doing here. And we have a test set that we use to evaluate our model. Typically, you have a big data set and you'd randomly split it into a large training portion and a small test portion. turns out that this MNIST data set comes with some test examples, and so we're just going to grab those. So we have a training set and we have a test set. And we're going to use our pre-process function that we wrote before. So this is exactly what we did before. And now we can actually evaluate how good our model is. And so we have our prediction. And we also have our loss. And then I'm just going to steal this here and see how that is. This is going to be y test instead. Test. So yeah, again, clearly this this model is not doing so well on the test set, right? So it got like 98% on the training set, but only 83% on the test set. And so this is still not bad, but it's not great. And this is something called overfitting. And so essentially, our model has memorized our training set and is not good at generalizing to our, I guess, out of training set, like our test set. And so how can we fight this? There are a couple of ways, right? There's a technique called regularization, which I won't cover in this workshop, but I would recommend checking that out later, which would help your model like generalize better. But there's also just using more data. We only use 500 examples in our training, and really using more data will help our model generalize better. So let's just try doing that. I'm gonna make xtrain and, oh, so you see here I imported a fresh xtrain and ytrain. This has all 60,000 examples. Let's pre-process those. And ytrain. And let's fit this. I am suspicious that I did not do the right thing. Oh, okay, yeah, I didn't do the right thing because I did x here, I need xtrain. So you're gonna see that this trains, oh. Let me just copy and paste the code from here so I know it's right. Cool. Oh. Okay. I'm not going to fix this bug. There's something wrong here. But essentially, it will take much longer for it to train to a good accuracy, but our test accuracy will kind of be similar. And we will be getting about 90% for our test accuracy. So apart from this weird bug, any questions about the stuff I just did? Or about overfitting, about these models? Yep.
Would it be like good to use a different data set? So you use the training set from like a library that was like made by those three people, right?
Yeah.
Could you use another one from a different source? Would that still work, or would that like not fit to the algorithm?
Oh, so yeah, this algorithm will work for like any sets of data that you like. It will work. This is like a pretty easy problem. There are like this is not going to do so well for like other problems. But yeah, you could definitely use like anything else. So there's a ton of other ones built in here. Yeah, I won't show them today, but I can definitely like point you to some other ones. Any other questions? Cool. So this is working not too bad, actually. A lot better than we kind of expected, right? It's doing like about 90% accuracy, or it should be doing 90% accuracy. Given this really simple model, it's just a line that we fit plus some function at the end. So this has a couple of drawbacks, this model. The first thing is it assumes some kind of linear relationship between our x's and our y's, because we are just doing a linear function followed by a softmax. And so there's something called a decision boundary, where the function determines whether like their class is like 1 versus 2 versus 3, etc. And so this can only model very simple decision boundaries, they're called. And also, this is not assuming any kind of interactions between variables, right? You're kind of assuming that each pixel in the image is independent. Why? Because it's just a matrix multiply some linear combination of those images. Really, we want to understand interactions between these images and these pixels, right? Because it makes sense. In an image, like pixels that are close together have some immediate effect on each other, whereas pixels far apart don't necessarily have that. So we're going to solve some of these problems when we introduce artificial neural networks. So from Wikipedia, what is an artificial neural network? I guess what you guys all came here for. So we have some long description here. Essentially, it's like it's some process that is inspired by the brain, where we're inspired by the connections of our neurons. And so let's kind of, but when you step back, a neural network is really just a function. We have some inputs, we have some predictions that we're trying to make, and this is going to be a function that models those predictions. So let's go back to our linear model that we were working with and think about how we can make that more complex and just better suited for the tasks that we're trying to do. So in particular, what if we just added more weight matrices? Oh, sorry. So what if we just added more weight matrices, right? Like what if we multiplied x by some weight, added some bias, and then did that over and over again? Well, you'll find that's not going to help, because really if you expand this out, you can just model this by the original linear function we had, where we have some big W that's like the multiplication of all these matrices, and we can similarly collapse B. So this is not going to get us any progress. But one thing we can do is the following. Sorry, I think I'm going to have to refresh this page. Sorry about that. Anyway, one thing we can do. Oh. Cool. So here, we can actually apply this linear function, then apply some nonlinear function, some activation. And then do this again, apply this linear function to the result of the previous, and then another activation. And then keep doing this multiple times and have some function. And so this, in essence, is what we call a fully connected neural network. Essentially, it's a bunch of linear operations followed by nonlinear operations, and we just stack these together. This function A that I was talking about is called an activation function. And so essentially, it's just some nonlinear function. That stuff is not supposed to be there yet, but it's okay. I'll type over it. So that is a fully connected neural network. This is a very simple type of neural network, and there are some really nice properties. First, it solves that problem of interactions. It will automatically find interactions between various explanatory variables for you. And by explanatory variables, I mean the x variables. What's nice is that a neural network is something that's called a universal approximator. There's an exact name. I can't believe it just slipped my mind. But essentially, given a neural network that's large enough, we're going to be able to model a function of any complexity. And so essentially, as these things scale up, we'll be able to model more complex relationships between our x and our y's. So yeah, any questions about what a fully connected neural network is? Yeah, so it's just a function. Take some inputs x, apply some linear, the nonlinear transformations, gives us your predictions y. Any questions? We'll actually start building this. Great. So let's talk about the nonlinear functions here. This is something I didn't talk about at all. There are multiple things this could be. In the past, things like the tanh function or the sigmoid function, which I'll actually just Google that, tanh. That looks something like this. These were pretty popular activation functions. But nowadays, one really popular one is something called the ReLU. So this is called a rectified linear unit. And so essentially, it's 0 when y is less than 0, and it's just a straight line after that. It's a very simple function. But this is what we use between neural network layers very commonly. Of course, there are others. Even though this seems linear to you, it's really not linear, right? When you get below 0, there is some change. And so this works surprisingly well for neural networks, and we'll see that soon. Okay, wait, hold on. Let me just get rid of everything below this. Okay, cool. So let's make a slight modification to our linear class before moving forward. And so the one modification we're going to make is the following. So before we had it generate a bunch of ones for our matrix, but now we're just going to do a random normal distribution. And the reason is related to gradient descent. So if we scroll up, I told you before that we are not guaranteed to find the best solution on our loss surface, right? There could be multiple minima. And so this is true for neural networks now. It could end up in a minima that's not desirable. So if we always initialize our starting place to be the same, we're kind of biasing towards one solution all the time. And so if we randomly initialize all of our parameters, then there's a better chance that we won't find a bad solution. Cool. So otherwise, this did not change at all. And now we're just going to define our neural network. So we're going to do that as a class as well. Fully connected network. And so essentially, we're going to define this in the same way where So before I move on, I did miss one piece of terminology, and it's something called layers. And so we see that we do this multiple times, right? We have this linear function, then this nonlinearity, then another linear function, etc. Each one of these groupings is called a layer. And so, for example, linear to nonlinear, that's like one layer. Then you have another linear operation followed by nonlinear, that's another layer. And so what I'm about to do here is create two layers. And the first layer is just literally going to be a linear, right? And I'm going to show you what this 50 is in a second. And then the second one is also going to be a linear. Input is 50, and the output is. So what is this 50? So 50 is called the hidden layer size. And so when we're talking about neural networks, I mentioned there are multiple layers of like linear, nonlinear, etc. And so the length of this output here, this is known as a hidden layer. And so 50 is the hidden layer size. And so, for example, this could mean that this little chunk of computation here results in a vector of size 50. And so this is the association between neural networks and deep learning. We say that machine learning with neural networks is called deep learning for this reason. We have these multiple hidden layers. Your terminology may differ depending on who you talk to, but I guess very commonly, deep learning is just machine learning with neural networks. So any questions about this hidden layer size? I guess it's kind of strange, but we can look at it more concretely. Okay, great. We'll definitely see this in action. And we're just going to do the same thing as we did with the linear model. We're going to track our trainable variables. And this is just the trainable variables of the first guy plus. So for those of you that don't know, each one of these is a list, and in Python, the plus operator concatenates the two lists. And so now this trainable variables property is just 4 TF variables that we're working with. And so now let's actually define what this function is. So take some input x, and we're going to do exactly what we did before. So first, we're going to apply our first linear function to our input. Then we're going to apply our nonlinearity, which is the ReLU that I was talking about. Then we're going to apply our second linear function to this. And finally, we're going to apply the softmax at the end. The same idea because we want this probability distribution. Cool. So any questions about this little chunk of code? I guess this was like the key point. Great, yeah. So yeah, this was kind of the key point of the workshop, right? Where we have finally built up to a neural network, but hopefully by building on these basic building blocks of linear models and logistic models, like this doesn't seem magical to you, right? It's just kind of an extension of what we've already seen. And so, yeah, let's train this thing and see how it goes. As promised, will copy and paste the last training loop I made. Where is that? Where is it? Oh no. Yeah, there we go. We'll just copy and paste this one. So you'll find, yeah, throughout the workshop, if you guys had your laptops, I would have made you write this yourself because we've done the same thing like 3 times, but I'll just do it here. So it's just literally the same thing as plug and play, right? I'm just going to call this neural network now, where we apply this neural network to our data. We already have the softmax. We don't need that. And trainable variables, and boom. Nope. Oh no. L1. I'm pretty sure our accuracy function is wrong somewhere. I'm just going to copy and paste the code here just so we have something reliable. Oh, this is why you don't live code for a demo, but let me see if I can figure this out. Just to fix this up, I'm just going to redo this importing of this data. And I'm just going to pre-process these again. And also for the test data, just pre-process that to make sure that's correct. True. Okay, nice. It's working now. Okay, really glad. So as you can see, it is taking longer to train because there is more computation that's going on. But eventually, if I let this keep going, this accuracy will do better than what we previously had for logistic regression. Yeah, it's only 1,000 steps, but you'll find that with neural networks, you do have to train for a lot more steps. So there are some things I did that are kind of arbitrary and not really clear, right? Like, why did I choose 50? Why did I only do 2 layers? And those are great questions and like big areas of research, right? What architectures are effective? What works well? How many hidden layers should you have? How big should each hidden layer be? And so by the end of this workshop, I will encourage you guys to just play with this. Add more layers, make each layer bigger, make them smaller, see what happens. For example, like maybe this doesn't even seem to make sense, right? We're starting with the size 784, we're going all the way down to 50, then 10. Maybe we want something in between. Again, this is something that you guys should definitely play with and build some intuition for by working with it. So yeah, do you guys have any questions about this training loop here? Cool. Yeah, that was kind of anticlimactic. Neural networks are not as spicy as you'd expect. Cool. So now we're going to look at what facilities that TensorFlow has to make this automatic. So I've kind of built this up from scratch, right? Like I made my own linear model class. I've made a logistic regression class, and I've kind of built this up. TensorFlow has most of this built in. So let's take a look at what's there. Not that section. Cool. So we created this model, this class that represented a fully connected neural network. TensorFlow has a tf.keras.model class, and so you can actually create your own class in this way, which I will show you here. And so we can do exactly what we did as well, except we get some of TensorFlow's stuff. And so when you call the super function, TensorFlow has some really nice properties that it'll take care of, which I will give you some examples. So if you guys haven't seen this before, basically we're calling the superclasses constructor, and so the tf.keras.model constructor will be called, and some stuff will happen. So we created a linear model in TensorFlow that is called a dense layer, and so that's literally tf. We import dense, and the reason it's called dense is, if you think about it, it's a matrix multiply is a densely connected neural network, right? Because each of the x inputs are going to be multiplied by a linear combination of each of the weights. If you didn't get that, don't worry. There are other kinds of neural networks where not all the inputs will be affected by the weight matrix. For example, there's something called a convolutional neural network. It does a slightly different operation. It's still linear, but there are some slight different semantics. So the reason it's called dense is synonym for fully connected, basically. Anyway, so the nice thing about this dense class is we don't actually have to define an input shape. TensorFlow will take care of this for us once we call it with input. And also another nice thing is that we can integrate this ReLU activation function right inside of this layer. And so this unit of computation basically represents this linear, then this ReLU, basically exactly what we did here. We can also create a layer 2, dense, and then we have our output length. We don't have to define the input shape, but if we want to, we could define the input shape to equal the 50 that we had before. And here also, if we wanted to, we could define input shape, which is equal to the input length. And the reason I'm making this a tuple is because that's what it has to be. It's a shape. Sometimes you can directly pass in images, and so they'll have like 2 dimensions, for example. And just like what we did before, we can define this call function. And so you'll notice this is not the dunder call. So here we had like this special magic method that let us call the class. Here, TensorFlow makes us override this call method because it gives you some extra functionality on top of that with the dunder call. And so we just do the same thing. We just return self.layer2, self.layer1 of x. And so we'll see that this has the exact same functionality. Oh, nope. What? Great. So this has the exact same functionality as what we had before, plus a ton of stuff, of course. One nice thing is if you call this model 784 and then 10, you automatically get these trainable variables. Oh, okay, it only creates them upon the first call. Okay, I'll show you guys that a little bit later. Cool, so this works exactly the same as what we were working with before. But you'll notice that our model is really simple, right? We just took the outputs from the previous layer and put them into the next layer. And so TensorFlow has an easy way of doing that as well. It's called a sequential model. And so literally we do model equals tf.keras.sequential. And then we can do dense, for example, 50 with the activation equal to ReLU. We can add more layers if we want, but I'm just gonna keep it at these 2. And we can do activation equals softmax, which is what we want at the end. Yeah, great. And if I think if we define an input shape, this should give us access to maybe, yeah. And so we have a list of the variables just like what we had before, and etc. So I'll give you a roadmap of what the rest of this workshop. So this is the core key concepts of this workshop. We're going to talk about how to train these a little bit more efficiently using the TensorFlow Dataset Api. Then at the end, we're going to talk about, we did like several lines of code. We could have done all of that in like 5 lines of code. And that's what this workshop's going to end with. And so I think I'll do like a 5-minute break and then we'll get back to it. Sound good? Any questions? No? Cool. You guys can come up and ask questions if you want. Let's take a 5-minute break.
Slow down. Yeah. Well, it's a lot of new information, right? Like I get this, I get all this stuff. It's a concept that it's super the first time. Yeah. Okay. That's sure. I can definitely like just repeat it. So we're good on time. Yeah. Going or repeating like this. Like we see it for an hour now. It was great. Yeah. It's a lot easier to follow than a regular lecture. And it's like you keep moving on, keeps you interested.
Yeah.
hopefully if you follow the link, like it has the full description and everything. Look at your comments, right? Yeah. Because since you're talking about reading the comments of the code. Yeah, exactly. So is there anything really new you have to kind of get when you first time? No. How'd you learn this? Yeah, like over time, there's like all my courses and so what kind of project? I've done some like machine learning applications on the handle. So I've tried like getting some data out of that.
During the break, is there anything you guys want me to go back and re-explain? I can definitely touch on something again while we're waiting. No? Cool, okay. Cool, I think I'll hop back into it now. So for this next part of the workshop, there are no new like concepts or anything like that. We're mostly going to be just making our pipeline a little bit more efficient, a little more realistic about how we do things. Also, if you're feeling like a little bit confused, yeah, no worries. Like the link I provided at the beginning, that I'll also provide at the end. I have like full comments with a little bit more detail than what I've said out loud. So hopefully that'll be helpful. And the document also has my email and Twitter and stuff. You can just DM me and I will definitely try to help out. So yeah, any questions about the concepts before we get into a little bit more of the syntax and the programming for TensorFlow? No? Great. So the next thing we're going to talk about is something called the tf.data API. And so far, what we've been doing is just importing these large arrays or tensors of data and just passing them straight to our model and using them all at once. And this is kind of problematic, right? The first thing is it's kind of slow. And so this may not seem slow to you, but this is a super tiny model. Once our model gets even slightly bigger, it's going to be very slow to work with. And so we need to solve that problem. The second thing is every time we do an update step, that depends on how big our data set is, right? Because we compute this loss with respect to our entire data set. And so as our data set gets larger and larger, it's going to be slower and slower for each step. And finally, in this case, we're lucky. This is a relatively small data set. We can fit it all into our memory. But there's a lot of times when data can't fit into your memory. You might have to read it from your disk, or you may have to load it from the web, whatever the case may be. And so we need to deal with these situations in a certain way. And so we're going to talk about something called mini batch gradient descent. And so this is just this gradient descent that we talked about, except instead of doing it on the entire data set, we're doing it on a subset of this data set. And so that's where the word stochastic comes from in SGD. we don't have to worry about that. And so it kind of works as follows. We have these mini batches of, let's say, size 32 to like 250, whatever the case may be. And we process the loss and we do our gradient step with respect to this small chunk of data. And we go through our entire data set and do update steps on different chunks of the data. And we're going to do this with the Dataset API because it's just easier. I'm just going to call this section tf.data. Cool. So I'm going to import the same stuff that we did before from the tf.keras datasets. Data. So you notice before I put like x train comma y train. If you guys are not too familiar with Python syntax, so I did this before. Now I just have that tuple inside this train variable. And so train is just 2 elements. So it's just a tuple of 2 elements type. Anyway, so yeah, it's a tuple. Anyway, so each of these things is a NumPy array. We want to convert it into a data set. And so tf.data has this data set, this function that will do exactly that. And so it works as follows. From tensor slices train. And we're going to do the same thing for test. So what is this train data set? So basically, this train data set contains all the images and the labels that we had before. Without any processing, it just holds it in this nice format. And now we want to do some processing, and we want to modify it to a way that we can train our model again. And so this involves the same steps, right? Turning this 28 by 28 into like a 1 long vector, doing the 1 hot encoding, etc. So I'm actually I won't copy and paste it, I'll type it out. So I'm going to define our preprocess function again, and I'm just going to add like a tf.data because that's what it is. It's going to take this x and y, and we're just going to do the following. We're going to reshape x. 28 by 28. So before, you notice that I did like -1, then 28 by 28, because we're working with the entire data set. This preprocess function, we're actually going to apply to the data set one at a time. And so the dimension is going to be 1 by 28 by 28, so just a long vector for each example. Once again, we are going to cast it. So I'm doing a tf.squeeze here. Don't worry about exactly what this does. We could talk about it afterward. It's not particularly important. And then we can also do the divided by 255. And I'm going to not do the 1 hot encoding for y, and I'll explain why a little bit later. So this is the same preprocessing steps that we did before, where we're reshaping our x and casting it to the correct type and scaling it down again. Cool. And so now, how are we going to apply this to our data set? So the TensorFlow Dataset API gives you some functions. So for example, we can map this preprocess tf.data entire data set. So map is kind of like a functional style of doing things. We have this function that will transform each example in a certain way. So in particular, we're turning x into a vector, and we're not touching y. And so this map function will essentially run this function through our entire data set. This returns a trained data set. Cool. So any questions about that before I start adding some more stuff? So essentially, we're doing the same transformations we did before, but in a TF dataset style. Cool. And so before I told you that we're going to be working with small chunks of data at a time, so we're going to write some code to make that happen. The first thing we want to do is we want to shuffle our data. I will explain why in a minute, but just know that we do have to shuffle our data when working with mini batch gradient set. And we're going to do some other stuff as well, which is like batching, for example. So batching is what I was talking about before. We're creating these little chunks of data. And right now we're creating chunks of size 256. And we're going to do this prefetch. So don't worry about it if you don't. So this is important, but not too, you don't have to think about it too hard. Essentially, we want more performance out of this data set. And so when the model is processing one example, we want it to grab the next one for us waiting. And so this is kind of like, it's asynchronously achieving this. And so that way, our model constantly has data feeding to it, and we can go much faster. And so this prefetch function tells TensorFlow how many examples to fetch in advance before the next. And what's nice is you don't even have to think about this. TensorFlow has this like experimental auto-tuning functionality where over the course of training, it'll tune itself and get you a good number so you can get some good performance out of it. For the test data set, we're going to basically do the same thing. Except we don't really care about shuffling because we're not training the model. I'll explain why we shuffle once again once I finish this code. So we don't need to shuffle. We just need to pre-process what's going on and then batch. Same size. So before I explain shuffling, are there any questions about kind of what we did here? Cool. Yeah, the tf.data API, maybe it's not my favorite API, but I think once you start working with it, it'll make a lot more sense. So shuffling. So I told you before, we're splitting our data set into little chunks, and then we're processing on each chunk. And we don't want to get the same sequence of chunks for every iteration of our training. And the reason why is we'll have some bias in what function we're minimizing, right? Like really, we care about the minimum with respect to the whole data set. But now we have some subset. We're trying to approximate the whole data set using this little chunk, and we don't want bias. And so by shuffling our data set, before we take these small chunks, every time we pass through the data set, each chunk is going to be different. And so that ensures that our training is not biased, and we're going to converge to a better solution. It's kind of the long story short kind of explanation. Finally, I'm going to scroll up and copy and paste the model code. And I'm also going to copy and paste the training loop from before because we're just going to do some slight modifications. So now we're using this TF dataset. It makes it a lot easier to work with this data. Previously, this X train was the entire dataset. And my claim is that you can't always do this, and so we're going to use small chunks. And so we're going to iterate through this just like we would expect to in Python. So XY in train dataset. So this is literally each XY is going to be one mini batch. And then we're going to do all of the stuff. Let me print XY. Actually, let me show you what XY is first. And so for those of you who are not familiar with Python iterators, you can do the following. Iterator equals, this is essentially what the for loop is doing, and then XY is equal to next. Don't worry if you don't understand this Python syntax. I just want to show you what the data set is outputting in our for loop. So X here is a batch size of 256, exactly what we said over here. And it's the vector of length 784, which is our flattened image. And it's exactly what we expected from before. And Y here is just the labels. And so I will explain why we didn't want hot encode in a second. And so essentially this represents the index at which the correct answer is, like what the correct answer actually is. So we iterate through this data set. Now, instead of doing this on this entire training data, we do it on just this little chunk. And we're going to change our loss function to sparse categorical cross entropy. So this is the same function as what we had before, but now it'll just accept an index instead of accepting a one hot vector. If you don't fully understand what that means, I would definitely recommend running my notebook code afterward. You'll clearly see the difference. But essentially, the one hot was the vector of size 10, where one index was 1, the rest were 0. Here, we're just listing the index. Cool. So that's sparse categorical cross entropy. Again, this is on the little y here. And this is also on the y. But we do have to make some changes. We're going to rename this to epoch. So now this loop is doing one pass over the entire data set. This loop is doing multiple passes over the entire data set. Every pass over the data set is called an epoch. And so here we're saying that, oh, let's do 100 epochs. And so 100 pass-throughs of the data set. And this loop is just going through each of the batches in the data. Before I continue, any questions about what I said? No? Cool. we do have to make one more modification to accept these indices instead of the one hot vectors we talked about before, and that is define a sparse accuracy. So if you remember our accuracy function before, expected 2 vectors, let me go find that and copy and paste it. Actually, I'm not going to copy and paste it. Let's just type it out. Sparse. Okay, anyway, so this takes a y true and a y prediction. And essentially, we're going to check if the y true is equal to So just to explain this once again, this argmax is finding the maximum value of the row. So for example, if your data had, let me show you a ypred. So this is like one example. So this tf.mat.argmax finds the index of the maximum value of this, and it does this for every row in the data set. Y true are these indices already? And so this function is basically saying, all right, is our prediction the same as what the ground truth says? And we're just going to return the exact same thing we did before, which is reduced mean of equal predictions. Oh, we have to cast this to a float as well. Yeah, I told you it's finicky with types. So remember that this equals equals is going to give you like a bunch of booleans. We actually want a number to take an average of. Any questions about this little function? It's kind of similar to what we did before, but different. Cool. And so we're just going to reuse this down here. Instead of using normal accuracy, we are going to use sparse accuracy. Are you guys familiar with enumerate in Python? So enumerate, I'll show you what that does really quick. So let's say we have x is equal to some list. X equals 10, 20, 30, 40. For x in, sorry, for val in x, print x. So this will print out. So this will print out each value in x. If we do enumerate, now we can get both an index and a value here. So now we get both the index it is and also what the value is. Super handy in Python if you guys didn't know. So anyway, I'm going to do exactly that right here, where we enumerate over the data set. And so this way we also have access to the step. And we are going to use this step because, bless you. We're only going to print every 100 steps, and so let's do that. Oh no, it doesn't work. I'm going to copy and paste once again from here because I'm not sure what's wrong with that one. Oh, I see why. So the reason is I did the wrong order of the variables. This is why I tend to use keyword arguments like this instead. Great. And so now you can't really tell, but this is trending much faster. I'm only printing every 100 steps, and the accuracy is going up pretty quickly anyway. And so kind of the lesson here is that even though we're not using the entire data set to get the most accurate depiction of our loss, we can still optimize pretty well. I will talk about one more thing. So this here is nice, but the problem is we're computing our stats only on the current mini batch, right, of size 256. So even though we're doing 100 steps, we're only computing the loss on the step 256. It'd be more ideal if we could just compute the loss on the last 100 batches, right? Like how well did we do on the last X batches, and then how well did we do again the next 100 batches, etc. The reason this wasn't a problem before is because before we were using the whole data set, but now we're only using a small portion. So our measures of accuracy and loss are not entirely accurate because we're using such a small set. And so we're going to look at what TensorFlow has built in to make it our life a lot easier to track the numbers that we want to track. And so I'm just going to call this section metrics. Cool, we're just going to define a little class to make our life easy. And basically this is going to compute an average. So it's going to initialize with an empty list. And basically we're going to do the following. We're going to keep track of a bunch of values over the course of training, and we're just going to append that to this list. The result is just going to be what the mean actually is at a certain given point in time. So we're basically going to return the sum of all the values divided by the length of the values. And so this is just the formula for average, right? We're taking an average over a bunch that we computed. And we're also going to make a function called reset states. So we only want to compute the average over a certain number of steps. After we compute this average, we can just throw away the old data and get the new stuff. Does everyone maybe this problem is not so clear. Does everyone understand kind of why we want to track this data over the last couple of batches instead of just the current batch? Do you want me to re-explain that? Try to do it again? Okay, so the problem here is this. Oh, sorry. So when I'm printing out this loss.numpy and this sparse accuracy, this accuracy is just on 256 elements, right? So before, when we were using the entire training data set, we had the loss and the accuracy on 60,000 items. Really, we care about the loss and the accuracy on those 60,000 items. The numbers we get out of this smaller set is just kind of an estimate of what it should be for the larger set, like a sample from our entire population. So this is kind of wasteful. We're only printing these out every 100 steps. It'd be nice if we can just say, okay, so the last 100 steps, there's 256 per step. That's like the last 25,000. What if we could just have the average over the last 25,000? And so basically we're reporting more accurate numbers, right? And so it's just more accurate. It gives us a better picture of how well our model is doing, and we can improve our model more accurately. Does that make more sense this time? Cool. And the way I'm going to accomplish that is the following. Basically, for every step, I'm just going to keep track of what the loss was. And then when I do want to compute it, I'm just going to take the average of what it was for the last X steps. It's pretty simple, but I just want to show you some TensorFlow built-ins that will help you do this easily. Let's go back and steal our model from up here. So we have this mini class that does some functionality for us. So again, we can instantiate our model. Oh, shoot, my scrolling isn't working. We're just going to copy this training loop once again. Oh, I did forget to do something. Oh, I'm not using model. I'm actually using this. Oh, we should be using model. So we're going to do the following. Basically, at every step, we're going to, so first we're going to create some loss metric that just computes, which is just a mean, and also this accuracy metric, which is also a mean. And we're going to do the following. At every step, every time we compute this loss, we are going to add it to our loss metric. So loss metric.add value, whatever this loss.numpy is. Same thing for the accuracy. Metric.add value, and we're going to compute this guy here. And now, instead of reporting the loss for just this mini batch, we're actually going to report the loss over the, so sorry, before I continue. So here when I do add value, basically up here, we're just appending that to this list of what we're keeping track of. And so I'm just keeping track of the accuracies that we've been using. And so now I can just do .result. And so this will compute the average over the last whatever number of steps. So for example, here it's 100 steps. Accuracy metric dot result. And this will give us a better idea of what's going on. Oh, one mistake. Also, after I do this result, I do need to reset it because we report this value, we're going to reset. So when I say reset states, so here essentially what we're doing is we're making this list empty again through the self.vals. So as you can see, yeah, it's doing a great job reporting this stuff. So any questions about what we did there? We're just tracking the mean over the last couple steps. And so the one thing that I did want to show you here is Tensorflow comes with this stuff built in. It's really simple. So loss metric tf.keras. So we have a mean metric here, and we also have an accuracy. Sparse categorical accuracy. And so these just make your life a lot easier. So you don't even have to do the NumPy version. You just call these functions. And yeah, this will take care of everything for you. So Tensorflow just has some facilities in there to track these numbers over time. So this training loop grew quite a bit. We had a very small loop in the beginning, and it grew to this larger and larger thing. Of course, as you do more and more complex things, it's going to get bigger and bigger. And kind of the punchline at the end of all this is it's actually super easy. We don't have to do all of that. TensorFlow makes it really simple to just do all these things yourself. And so here, I'm importing this data. I am just normalizing like I did before. I'm creating this model, which is super simple, just a sequential model. And here's the fun part. You can compile this model with an optimizer. So for example, we were using SGD. We had a loss function, which is like categorical cross entropy, and metrics we want to track, which is accuracy, which we just worked on. And now we just call this function model.fit, and we have our X data, our Y data. We specify batch size, epochs. Validation data is the same as the test data we were talking about. Oh. Yeah, now this is super easy and it's super fast and performant. So in the backend, essentially it's doing some stuff where there's some optimizations that go on where you can basically put a lot of functionality into C and into their graph execution platform in the backend, which makes it very fast and very easy. And so we kind of deconstructed everything and we learned how things work end to end. But when you really want to do this stuff, it's simple. It's just a couple lines. And I would encourage you to use this API as much as you can because it prevents mistakes and it's fast and easy. And so I guess your homework today is just when you want to try this stuff out and understand, what models and architectures work, use this stuff. It's going to be easy and you'll be able to experiment very quickly. And so the conclusion today, we covered a bunch of things. We understood like linear models and logistic models. We extended those to neural networks. We understand how gradient descent works. And we kind of understand the various parts of the TensorFlow API, working with data sets, working with metrics, etc. But of course, this is an introductory workshop. There's a lot more out there to learn. And these are some topics that I would recommend looking into next. The first one is backpropagation. And so we kind of just blindly use TensorFlow's automatic derivatives, like, hey, we can get derivatives if we want them. But backpropagation is actually how that happens. And essentially, it's chain rule, but I would encourage you to look into it if you're interested. There are different kinds of neural networks, like convolutional and recurrent. And so basically, convolutional neural networks work very well for image data, and recurrent works really well for sequence data. These are definitely better suited for various tasks. And also regularization. Hey, my model's overfitting even though I'm using a ton of data. How can I stop this? There are various techniques to make sure you can regularize your model. So that's on the neural network side. On the TensorFlow side, there's a ton of stuff to look into as well. I just use dense layers and activation functions here. There are so many layers that you should be looking into and checking out. Oh, in particular, even in this last example, I didn't even flatten my images, right? There's a layer that would flatten my images for me. And so just looking into these and understanding what's in your toolkit will definitely help you out. I showed you a couple ways to build models in Keras, which is like making a class or making this sequential. There's also a functional API that could be useful to you. There is something called tf function. And so basically, if you create a function with a bunch of TensorFlow operations, there's a decorator in Python that's called tf function that'll speed up your code dramatically. And I did not cover that today because it's not necessary for a beginner workshop. But if you really want fast training and fast inference, this is what you got to use. And finally, like distributed training. If you want to do multiple GPUs, multiple devices, like that's the way to go. So I hope you learned something. I will scroll back to the top to get the link for you guys about what for this workshop. I definitely recommend going through it afterward. And yeah, feel free to talk to me after this or reach out later. Thanks for coming. Cool. Any questions? Great.